Hello, everyone. My name is Brian Troutwine, as was mentioned. I am a fault-tolerant real-time systems engineer. I am interested in domains where there is some sort of disastrous consequence if you fail. So industrial control, financial systems. I also do a lot of research because it's very difficult to sort of get practical experience with disastrous systems. So one thing that I research quite a bit is the Apollo project. It's extensively well documented, and it has a lot of different areas that you can dig in. In this talk in particular, I want to discuss the Apollo guidance computer. But before we do that, we need to talk about the domain that the guidance computer sits in. The thing that I find very interesting about critical systems is they are often not separable from the organization that creates them. They are often influenced by the problem that they solve because they're custom made to solve a very particular, very pernicious sort of problem. Oh, my computer just chirped at me when I tried to move. That's fun. So this is the Earth. This is our planet. In the 1960s, it was attempted by a few different governments, the United States and the Soviet Union, to get to the moon. It actually worked out for only one of them. The moon, it turns out, is actually quite a bit of ways from the Earth. It's 400,000 kilometers. And the tricky bit about getting to the moon is that you want to do it in a controlled fashion. And to do it in a controlled fashion, you need to do it in a relatively safe fashion. It's relatively simple to collide something with the moon, but it's very difficult to get something that can stop at the moon. One of the very early projects to try and get something to the moon was by a rocket scientist, American named Herman Oberth, who was one of the first people to build a liquid fuel rocket. And his plan was to build a liquid fueled rocket that would take 100 tons of TNT up to the moon, and it would collide with the moon and then blow up, and we could sort of train a telescope at the moon and see the explosion and say, yeah, we touched the moon. But the project to land people on the moon and then return them, not a one-way trip, was rather difficult. So the Apollo project, which was the project in the United States, it was carried into orbit by the three-stage Saturn V. And so there are really two things that you talk about when you talk about the Apollo project. One, you talk about the lift vehicle, the device to get the spacecraft into space, and that's the Saturn V. And this is not really a talk about the Saturn V, although the Saturn V itself is an incredibly interesting engineering project. But we're talking about the spacecraft. So the Apollo craft is carried into space. You start dumping stages. Here you see Apollo 8, one of its interstage drops. So staging just means you keep cutting the rocket into pieces. Once the Saturn V finishes its work, or it almost finishes its work, you're in low Earth orbit. So you're now actually in orbit around the planet, and you are almost a spacecraft. So the crew starts going through their system. They have these checklists, and they have to confirm that the machine is operating as, they have to confirm that the machine won't kill them. If in fact the machine would kill them, according to their system checks, then they go back down into the atmosphere. But if everything checks out, the final stage, which is the third stage, boosts Apollo into a free return orbit. So this is a thing called a trans-lunar injection. So you sort of burn opposite to where you want to go, and you keep raising the opposite side of your orbit, sort of like that. And then in the end, you get a free return orbit. So it's called a free return because, in fact, you get a free return. This saved the crew of Apollo 13. They popped an oxygen tank, and had they not been on a trajectory that would just naturally carry them back, they would be a memorial in space to human folly. There were other options. So there was an approach that was called direct descent. So direct descent is pretty much what it sounds like. You just build a really big rocket. So Saturn V was so big that the blast trench, where the Saturn V sort of ignited into initially, had to be made of specially reinforced concrete. And it had to be made of specially reinforced concrete because the Saturn V was so powerful when it took off that it would cause the concrete to burn. And the concrete didn't burn because of the rocket fuel, although it was very hot. It actually burned because of the sound of the Saturn V. So direct descent, instead of sort of making this nice orbit, just launches you in a ballistic arc to the moon. Now, the problem with doing that are twofold. One, you need a much larger lift vehicle. So there would have been a larger rocket than the Saturn V called the Nova that would have been built. The other problem is that you're obligated to go to the moon. You can't turn around. You can't make system checks. So already, even before we get into the spacecraft itself, the parameters of the mission are designed for a particular thing, for having fault tolerance, for having the ability to say, things have gone poorly, let's back out of this. So once the Trans-lunar Injection is done, once the free return orbit is established, then you have to build the spacecraft. And the spacecraft has to be extracted. So you see here on the very bottom, the final stage of the Saturn V. So this is the last thing that the lift system does. And it holds, in these three arms that sort of swing up, it holds the bottom of what's called the service module, which you see detaching here on the left-hand side, in place. So those arms come out, and then the service module and command module, which is where the astronauts are, sort of moves up. They turn around, and then they descend back, and they have a docking clamp, and they dock with the top of the lunar module. The lunar module is the thing that descends down to the lunar surface, and it's its own independent spacecraft. And then you have a spacecraft, and this is Apollo. So this is really what we're talking about. It is only partially designed for atmospheric flight and only ballistic atmospheric flight, but the components that you have here going from my extreme left to right are the service module, command module, and then lunar module. And the lunar module itself is composed of two pieces. One descends and then one ascends. So space travel is a tricky business, and it's a tricky business because there's a lot of explosives involved, there are a lot of dangers, but in particular what we're going to be concerned with in this talk is that orbital paths that you take are a narrow balance of accelerations, so it's very difficult to get these right. Too little and you miss your goal. So if you're trying to get to the moon and you don't thrust enough when you do the TLI, you just sort of make a big loop and then you come back. Too much and you also miss your goal. This is actually probably the worst one because after this point, you are now orbiting the sun, which is, again, you become a memorial to human folly. So the guidance control system of a spacecraft is very important, and it must answer three questions. Which way is up, which is kind of an interesting question to ask in space. We mostly just have to choose a reference frame, a universal reference frame, and just arbitrarily declare that this is up, this is down. Where am I? Obviously space, but exactly where am I in the reference frame that I have now decided? And where am I going? So what is my vector of acceleration? What is my attitude? Things like that. These questions are so difficult to answer and so important to always be able to answer. Because if you can't answer them, you die. Like that, let's be clear about that. You die if you can't answer any one of these questions. So because of that, Apollo has three triply redundant ways to answer these questions. So the first is very interesting. The first is called the Deep Space Network. So it is an global network of long-range radar stations. So they're big radar dishes. You can actually, some of them are repurposed radio telescopes. And they're scattered all over the globe in the 1960s. Partially, they were funded by the US military and European nations to detect the launch of intercontinental ballistic missiles. And then they got repurposed and purchased by the civilian agency NASA. So you can sort of see a map of coverage here. In the 1960s, they did not cover the whole planet. And there were no satellites to speak of. They tended to be relatively small things that died quickly. So if you ever watch something like Apollo 13, you know, there's that dramatic moment where they go behind the moon and there's no communication and they're all very worried. That's because of the Deep Space Network was totally localized on the Earth and only in certain positions. But they tried to arrange these antennas so that they mostly had coverage. Nowadays, if we were to go to the moon, we would just park a satellite on the opposite side of the moon and always have perfect conversation back and forth. So Apollo carried a high-gain antenna. So this is the view of the Apollo command module from the lunar module when they're redocking. And that's the high-gain antenna, and it's always pointed at the Earth. It always tracks. The computer controls the tracking, although it can be manually controlled. The other method is celestial navigation. So this is kind of an interesting one because we've been doing celestial navigation as a species for thousands of years, at least. And the celestial navigation in the Apollo spacecraft is very interesting because the methods that we use here on Earth don't apply. So if you've ever used a sextant or an astrolabe, it has an implicit horizon. So you measure the angle of two things between the horizon, but there is no horizon in space. So what did they do? Well, they have two things. The first thing that they have in the Apollo spacecraft is a telescope. And it's actually kind of weird to call it a telescope because it's a 1x magnification telescope. It's actually a window. And then they have a sextant, but there's no horizon. So what do? They have these mission time star charts. So everything is so carefully planned out that they have the ability to say, when you look out of your telescope/window, you'll see stars. And the navigator, and there is a navigator in the Apollo spacecraft, is obligated to take the sextant and then measure the angle between these stars. And that provides an artificial horizon, so to speak. So here you can see the inside of the command module. Sort of down at the bottom of the command module is where the seats were. And I say bottom, and there actually wasn't that much space. It's really the size of 3 or 4 telephone booths. Down at the bottom were where the benches where they would ride, and they would fold the benches up so then they had room to work. And you see the housing for the telescope. The navigator would then sort of float up to where the telescope and the sextant were, and then do the work. And then periodically, that would be redone. There was a thing that had to be continually updated, and it was continually updated either by the Deep Space Network or by the Celestial Navigator, called the state vector. And this was held by the computer. So the state vector is really just the answer to those 3 questions. Where is up? Where am I going? And where am I pointed to? And each one of these methods could update the state vector, and the ability to independently update them inside of the spacecraft actually saved, again, the Apollo 13 crew, because when they had to shut everything down, they could no longer get telemetry from the Deep Space Network. The last method that you have for updating the state vector, updating these 3 questions, is dead reckoning. Ooh, laptop. Is updating is dead reckoning. So dead reckoning is, again, something that we've been doing on the planet Earth for a long time. The basic idea is that you have inertial guidance. So this is an inertial guidance unit that rode in the Apollo spacecraft. The basic idea is it's 3 interlocking gimbals. A gimbal is basically a very sophisticated top, and it spins all the time. And then if you have acceleration, it causes the gimbal to move just a little bit. And from that movement, you can tell what the force and magnitude of the acceleration were. And from that, if you know where you started, you can continually update your location. So they use 3 gimbals. And if you ever read about how fighter airplanes work, they also use dead reckoning. But they tend to use 4 gimbals. And they use 4 gimbals because they want wild ranges of motion. They want to be able to do loops and things like that. But it was assumed by the engineers that planned out the inertial guidance unit that the Apollo spacecraft would never need to do these wild maneuvers. It turns out that the trade-off here, and there is in fact a trade-off, you save about 50 pounds, which is very important on spacecraft, saving weight, but you risk gimbal lock. So a gimbal lock is where 2 or more gimbals enter the same plane. And once they've entered the same plane, say X and Y coincide, now you can't tell the difference between movement along the X plane and movement along the Y plane. So you have to reorient the gimbals, which means shutting them off and then using the sextant and the telescope to get them aligned again, which takes a long time and is very difficult to do. In a few cases, they actually did gimbal lock the spacecraft. Apollo 11 did it on their way back, and I believe Apollo 16 did it. So the person that designed this inertial unit actually regretted very deeply designing it in this fashion. So that's dead reckoning. The dead reckoning unit sits pretty much below the celestial navigation because everything sits close together because it's 3 telephone booths and an aluminum balloon. So the Apollo guidance computer integrates all 3 of these systems. It integrates each one of these things. It is possible to manually fly the Apollo spacecraft, and it was discussed very heavily in the early days of the design how much of the Apollo craft should be automated. And in the United States, in NASA at this time, there was an ongoing debate between 2 different types of groups. One group was represented by Marshall Space Flight Center, Wernher von Braun's group, and they wanted something purely automatic. So you would just sort of load citizen scientists or Wernher von Braun himself into a spacecraft and you would get to go to the moon, and the machine would just take you there. Now that's great. It's very efficient. It's very convenient because you can put pretty much any goofball in the spacecraft, but as soon as something goes wrong, you are a memorial to human folly, because an automated machine can only deal with situations that it was designed to deal with. It can't improvise. The other sort of group, which was closely associated with the astronaut corps, was a completely manual spacecraft. So the astronaut corps in the United States was composed primarily of test pilots, and they were very used to having control of the machine. So they wanted to manually fly the Saturn V lift system, they wanted to manually fly the Apollo spacecraft, which was possible in part. It turns out that it's practically impossible for a human to fly a rocket. It is possible for a human to fly a spacecraft, but it's so tedious and so difficult that you can't do anything else. You are continually obligated to continue the maintenance of the spacecraft, and the Apollo was intended to eventually be for scientific purposes. So you could not choose to put a scientist in because they wouldn't be able to fly the spacecraft. So the Apollo was designed to be a hybrid system where you have pilot in the loop. And the Apollo guidance computer was central to that because the AGC is what the pilot basically flies. It becomes a secondary crew member or a fourth crew member that sort of relieves the tedium of daily ship operation, but gives the human pilots the ability to intercede at will. So the Apollo guidance computer is sort of sitting in the middle of all of these things, and you can kind of see, you have the telemetry that you're getting from the Deep Space Network, you have the inertial guidance unit, you have the Apollo issuing commands for various things, so it's very busy all of the time. And it also happens to be the fly-by-wire control computer. So there are actually two computers in the Apollo spacecraft because there are actually two spacecraft in the Apollo spacecraft. There's one computer in the lunar module, which goes down to the surface of the moon, and there's one computer in the command module. And they have slightly different purposes, although they were made out of the same hardware and shared a lot of the same software. So all of the human operations are also interceded by the Apollo guidance computer and interpreted. So now we don't think too much about fly-by-wire systems. Every jet that we get into, the pilot doesn't sort of manually control servo motors. The pilot is controlling a computer that controls the servo motors. At the time, Apollo was only the second fly-by-wire craft ever made. The first was the X-15, which was also a NASA research project. So it was sort of a bold leap. And it was even more of a bold leap in that the Apollo computer itself was so new. But we'll get into that. So the Apollo guidance computer also manages all of the analog and digital displays. So it controls everything that the astronauts see. It is the sole source of truth for an astronaut in the AGC. Once you shut the AGC off, say what happened in Apollo 13 to conserve power, you shut off all of the sources of truth. All you've got left are announcements from the radio from ground control. And that's the main control panel. And the Apollo craft inside is hugely complicated. So you see a lot of switches and dials and toggles because it's the 1960s and everybody likes switches and dials and toggles. But there have to be checklists for controls. And this is all underneath controlled by the computer. So even when there's a toggle or there's a dial that moves back and forth, that is controlled by the computer. And it actually turns out that it's incredibly hard to get a computer in the 1960s to correctly move a dial in all cases. So the AGC, it does all of these tasks. It is one of the most critical components outside of the engines in the Apollo spacecraft. And it does all of this work with 5 interrupts. And it has a 2 megahertz clock, which is kind of a joke because each instruction takes 2 cycles to complete at least. It has a 16-bit word, although one of the bits is parity bit, and then there is an additional bit that is check bit. So really you have 14 bits of data to work with. You have 2048 words, and I didn't accidentally drop a K there. You have 2048 words of RAM. You do have 36K words of ROM, and 17 registers to work with. And the AGC weighs 70 pounds, and it's 1 meter cubed, and it draws 55 watts, which is about the same weight, or same power draw as a laptop, and about the same weight as, I believe, 70 laptops. So to give you a comparison for computing in the 1960s, this is the real-time computing complex. So this is the complex inside of Houston Space Center, was at the time, that received all of the telemetry from the Deep Space Network and then computed the state vector. So if you'll recall, the AGC is also obligated to compute the state vector. So this is multiple tons of computing equipment. I have no idea how much power it draws. It required its own refrigeration unit, and it's doing the same job as the AGC. It uses vacuum tubes and some integrated circuits and things like that. But you can see that the Apollo guidance computer at the time is sort of a very special kind of machine. And the AGC is a digital computer. It's not the first one. There have been others. This is ENIAC, but it is one of the first to use integrated circuits. So this integrated circuit doesn't look like the sort of integrated circuit that we're all familiar with, in part because they're gigantic, but also because they're called flat pack. It was difficult for them to layer silicon correctly, so these were partially manually constructed. And the only other computer that I'm aware of that used integrated circuits in any sort of real sense was the computer in the Polaris rocket. So in the image for the Dead Reckoning, I don't know if you were able to recognize him, but that was President John F. Kennedy, and he's looking at a contrail. That contrail is made by the Polaris rocket. The Polaris rocket was a weapon of war. It was a submarine-based nuclear delivery mechanism. So it was built to have a computer in it, because submarines tend to move around, and you have to continually update the location of the rocket, and then the rocket has to be able to compute its flight path at need. And that was one of the first, if not the first, computer to use integrated circuits. The same people, actually, that made the Polaris rocket made the AGC. So there's direct lineage there. So the Apollo craft is very unusual, or the Apollo guidance computer, excuse me, is very unusual in that its ROM was made out of what we call core rope memory. So core rope memory is a magnetic donut, several 100,000 magnetic donuts, and then copper wire threaded through them, or weaved through them. So when the Apollo guidance computer programmers would program, when they assembled their program, the output were Mylar punch tapes. And those Mylar punch tapes would then be fed into a looming machine, which would then weave the copper wire through all of these magnetic rings. So this is the AGC. So this is the AGC and the DSKY, which is, so the AGC is that sort of vaguely metallic blob there, and then the other component is the DSKY. So the AGC was very unusual for the time in that it was interactive. There were some research computers that you could sort of go up to and interact with, but the AGC was designed to be interactive in an extremely stressful situation. It was designed to be something that you could query, that you could get information of, that you could set tasks to. And the main interface for the computer was what was called the DSKY, which stands for display, keyboard, or display and keyboard. It's sort of hard to get the scale of the DSKY right in a talk, but it's one of the first interactive computers, and it's the first computer that's designed to be worked with sausage fingers. So you had to be able to work this thing while you have space gloves on. And I don't know if any of you have ever seen somebody wearing a spacesuit. Spacesuits are not very good for our fingers. Our fingers are very weird, and it's difficult to get it right. So each one of those keys is about this big, or about the same size as one of the coffee cups that we have at the conference. And so that's the DSKY, and it allows the AGC to give fast updates to the astronauts. The astronauts could sort of punch in a program, and the display would continually update. It looks a little bit like a digital display, like an LCD. Those hadn't been invented yet. Actually, this display, if you've ever been in a ferry building or a train, and you have those little like flipping mechanical relay things that go, that's what the DSKY did. So they were luminescent because there was a light bulb behind there. And it allows the astronauts to run select programs. So if we sort of zoom in, up at the top, there's a few things to see here, and it looks obscure because we haven't been trained to use the DSKY, but it's running program 00. So you see in the top left-hand corner for me, prog stands for program. There are different programs. 00 is the program that runs when you're on the launch pad. It is the program that does all of the system checks for the Apollo guidance, or for the Apollo spacecraft. Verb is the command that you're giving to the spacecraft, and then noun is the information that you're giving to it. And then below that are the readouts that the DSKY is giving to the astronaut. There's actually no notation for decimal points, so if there is a point where an astronaut will get information that has a decimal in it, the astronaut is just expected to understand there's a decimal point at a certain place. So also on the left-hand side, there were status indicators, and these status indicators were driven by different interrupts. So you can see underneath temp, gimbal lock. So when you would fly close to gimbal lock, the computer would recognize it and start sort of beeping, because the computer was meant to help you. The computer was not subordinating the humans, but it was trying real hard to keep you from killing yourself. So what is the computer actually doing back there? It's a primitive machine by our standards, and even at the time, it was, by the late 1960s, once it flew, it was considered a primitive machine. It was designed in 1962, and then relatively unchanged in its basic architecture through that time. So this is a view of the Apollo guidance computer's interrupts in 1 second. The first two interrupts are called time 1 and time 2. So these give elapsed mission time. So time 1 overflows into time 2. So time 1 ticks over once every 10 milliseconds, as I recall, and then eventually that overflows into time 2. So remember, these are relatively small words, and if you do the math, it turns out that you run out of time, your time flips over on itself again after 30 days. But the missions were so short, there were 2 weeks at most, that it never mattered. You would never get up to 30 days. You also didn't carry enough oxygen to get up to 30 days, so there would be no one around to care that the clock had now gotten weird. So this is the interrupt for the wait list, and the wait list runs every 10 milliseconds. So we'll sort of get into this shortly, what exactly the wait list does, but fundamentally, what this interrupt drives are the lowest level tasks of the Apollo guidance computer. So attitude control, making sure that the AGC is pointed correctly, making sure that oxygen is flowing correctly, things like that. So this is T4rupt. This fires every 20 milliseconds, and these are for synchronous I/O operations. So the AGC is an embedded computer, and it has relatively low processing power, but it has very high throughput. So there are a lot of analog systems in the Apollo guidance computer, or in the Apollo spacecraft. You have RCS, reaction control systems that allow you to move in space, and those have to be fired in a very specific fashion. You have radar, you have uplink activity, you have a lot of different things that are going on, and that interrupt is what drives them, and it goes in sequence. So there is a program sequence in the core rope memory of the order that these go in. So it's round robin, we would now call it. And then you have the digital autopilot, and the digital autopilot runs every 20 milliseconds. So this is something that uses the modifications that the T4rupt routines make to make adjustments. So if the T4rupt interrupt decides that, well, we're at this attitude and whatnot, the digital autopilot is able to look up its mission spec, decide if we've deviated, if the spacecraft rather has deviated from that, and then fire the engines or fire the RCS jets more likely. The digital autopilot is also used during landing, so it was a dual purpose thing. The digital autopilot is unusual in the AGC software system in that it runs from anywhere between 10 milliseconds, which is a relatively short duration, to 120 milliseconds, which is considered to be an eternity in a machine that's so slow. And what the AGC does, because it runs every 10 milliseconds, it's relatively coarse. It runs every 10 milliseconds and it has relatively long running duration. It's able to program another interrupt, time 6, and that's called the fine scale clock. The fine scale clock actually has sub-millisecond resolution. So if you're burning a rocket engine and you're trying to maintain these delicate balances of operation, or of acceleration rather, you don't want to burn for 10 milliseconds if you really need a 1 millisecond burn. So that's what the fine scale clock is meant for, and it's entirely to be used by the digital autopilot, or the DAP. So time 3, time 4, and time 6, they're all programmable. So they can be manipulated by the onboard software. So nowadays, what we would call the AGC is a priority scheduled real-time embedded computer, which is sort of a jargony way of putting it, but at the time they had no words for it. They invented a lot of the things that go into these sorts of computers. So priority scheduling, how does the AGC do that? And it's worth pointing out that priority scheduling was controversial. Any sort of computing task that people did at that time, if you had to do scheduling, it tended to be either batch, which means you just sort of shuffle down with a box full of punch cards and you have someone feed it in, or they tend to be round robin in the case of business machines. That's was what people were most familiar with. The Polaris, which the MIT instrumentation laboratories worked on, both the Polaris and the AGC. The Polaris was the first priority-driven, priority-scheduled computer. Hal Lanning was the engineer that developed priority scheduling, and then Hal Lanning was brought to the AGC project and brought priority scheduling with him. So 2 tables exist for jobs in the AGC, and the first is called the wait list. And the wait list allows only jobs that have less than 4 milliseconds of execution. Now, in the AGC, there's no way of enforcing these invariants. There's not enough resources in the system to allow you to say that a job will be killed at 4 milliseconds. You can keep running if you want. So all of these invariants that I discussed have to be extensively tested. And the way they tested was interesting. They had a Honeywell mainframe that could simulate the AGC, and then they had a full mock-up of the spacecraft that they would put astronauts in. And then they would have the astronauts run through a mission, running the test software, and if the astronauts were killed by the computer, then they knew they had a bug, and they had to go back and fix it. So there are only 9 tasks the waitlist can do. And if you remember, the waitlist is the lowest fundamental core. There's no operating system to the AGC because the MIT Instrumentation Laboratory hadn't heard about operating systems yet. But you might think of this as the lowest level kernel tasks, the thing that catches interrupts and such. So there are only basic instructions. The basic hardware instructions in the AGC are available to you. And the AGC is relatively restricted in terms of instructions. Add, subtract, divide, multiply, fiddle with this bit of memory, do that to this bit of memory. But that's basically it, which is fine for an accounting system. But when you're trying to figure out how long to burn a rocket or if your rendezvous is going to work out, it's not enough instructions. So there's no rescheduling. The waitlist is encoded in the ROM. It's encoded in the core rope memory. So one way of enforcing these invariants was just to keep running them on the ground. Then you would know that there was no modification that could be made. And there's no executive. We haven't talked about the executive. So the AGC software provides 2 operating abstractions. So it's very difficult to write any sort of real problem in the basic facilities provided by the machine. So to get around this, to get themselves closer to spaceflight, when they were programming the device, they built these abstractions. And the first is the executive, and it runs low-level routines. So it handles things like interrupts on the DSKY when an astronaut presses a button. It handles that. It handles things like uplink activity and storing into the appropriate registers, and it handles system restarts. So the AGC is a fault-tolerant computer. It has the capability of realizing that some things have gone disastrously wrong. Perhaps you've tried to allocate something that couldn't be allocated, and just causing the entire computer to reboot itself. It handles supervision. So the executive has enough high-level instructions in it that you can say that this job should have some sort of invariant. And that invariant, if it's not held, should be killed. Or if this job has failed, it needs to be rescheduled. And it keeps the core set. So we haven't talked about the core set. The core set is another layer of the abstraction, and it has 12 tasks. So the executive, when you run a program, you can say, well, I'm only going to execute for 10 milliseconds, but I need to do a thing that will take a minute. So you put it in a queue, and that queue is periodically run when there's nothing else to do. And that's the core set. And there's only 12 tasks that you can put in it, and it's dynamically programmable. By convention, the engineers were not supposed to go past 11 tasks. But it turns out there's actually nothing from stopping the core set to fill up. What the executive does is it just sort of finds the next place where there's a core set slot and puts a task in, and then if there's not a slot, it just issues an error up to the astronauts. So most invariant guarantees are left to analysis and testing. And in testing, they never run into a case where the core set filled up. But it actually turns out that the core set did, in practice, fill up on occasion, the most notable of which was the Apollo 11 landing, where they're sort of landing for the very first time, and there is a computer alarm that suddenly the core set is filling up, and people are freaking out because they might have to abort the first lunar landing. But it turns out there was basically a short in the computer. So at first, people blamed Buzz Aldrin for leaving a radar on that shouldn't have been left on, but it turned out that that had nothing to do with it. There were 2 wires that ran beside one another, and they were slightly in phase with one another. And one of those wires happened to be the feed for the radar rendezvous system that caused that to register in the computer as continual information about radar rendezvous. So the computer was actually tasking itself up to 80% of its computation ability to try and figure out what the next rendezvous was supposed to be, which obviously they weren't going to rendezvous, they were trying to land. So had the AGC not been designed as priority, had it been round robining, they would have crashed on the moon, because there would have been no ability for the computer to say, don't worry about that, we're trying to land right now. So the core set is priority ordered. When the executive puts something into the core set, it says this is more important than that, and that's how it works the ordering. So each time there's an interrupt to cause a search for the core set, it just does a linear search and then finds the thing that's most highly ordered and pulls that off the top. So this goes through every 20 milliseconds. If you need something more fine-grained, you have to flip it over into the fine-scale clock. And you have the option to use the interpreter. we haven't even talked about the interpreter. So this is the last abstraction that the Apollo guidance computer programmers made, because at each step they realized that the instructions from the AGC are very primitive. You can't do much with it, and it's very difficult to write good quality software that doesn't kill people if you have to express them in these really, really low-level routines. So in the AGC, they built extra instructions in software. So what they would do is, in the executive, you would call the interpreter, and you would give it basically what we would now call a string. And that string was full of instructions. And these instructions would be things like arctan, or time to target, things like that. And that allowed the software engineers to, in their interactions with the astronauts, in their interactions with the mathematicians that were figuring these things out, to program closer to the domain of the problem set. So the AGC only had a word size of 15 data bits. 14 if you don't count the parity, which, because you have total control of the computer, sometimes you can ignore the check bit. Sometimes you can ignore the check bit. So that was insufficient for accuracy in spaceflight. So what they decided to do was, in the interpreter, you now have double wide words, which have to be mapped into 2 extra words, but the instructions know to just sort of mask that, where if you're working in the executive, you have to fiddle that yourself. So the interpreter carries these high-level routines, and they actually called them routines, what we would now call functions. The ability to say, figure out how long it will take, how likely am I, or at what time will I crash into the lunar surface if I don't slow down, things like that. It has a rich instruction set, so arc, cosine, these things that are very important when you're doing celestial navigation, but not so important when you're just trying to fiddle with tasks. And it has extra wide words, added accuracy. It turns out that the extra wide words, what they called extra wide, impossibly wide, was 32 bits. And if you sort of do the math on it, 32 bits with 2 obligatory data bits taken out is not enough accuracy to get anywhere past the moon, but it's more than enough accuracy to get to the moon. And in working in the interpreter, you had a radically simpler programming model. So long as you could get all of the bugs out of the interpreter, you could write smaller, more compact programs that could then be analyzed more easily. So one difficulty they found early on was trying to work everything out in the basic instruction sets was that they could introduce bugs, and they could introduce misunderstandings that the programmers had, because they were mathematicians that had focused on machines and were not orbital dynamicists. They were not pilots. And so they would introduce deviations from the mental model that the pilots or the orbital dynamicists had. And once they compacted the instructions into something that was more direct, they were able to communicate better and understand where they had messed things up without killing astronauts. So this is a free return orbit. This is the orbit that we were discussing earlier. And if you're going to get into the moon, you have to do what's called a capture braking. And that just means firing opposite to your acceleration. And when you fire, you pull your orbit in until suddenly you are captured into the sphere of influence of the body. And this was entirely controlled by the computer, because the delta V and the pointing, the delta V is the ability that you have to change your velocity, and the pointing necessary was so precise that a human in simulation couldn't get it right. They tended to just kill themselves or descend the entire thing into the surface or suddenly orbit the sun. So now you're in lunar orbit. And up to this point, loss of the command module computer hasn't been abort-worthy. So they could lose the command module computer and continue the mission, but it's a different matter for the lunar module. So the lunar module is absolutely essential to a controlled landing on the moon, and it's because the lunar module is entirely fly-by-wire. Landing on the moon is so difficult to get right manually that in simulation, very few people were actually able to do it. One of the people that was capable of doing it was Neil Armstrong, and he only managed it a few times, but that's why he got the nod for the first lunar landing, because they didn't know if the computer would fail or not. So this is the lunar module. It has deorbited itself, and it's now descending to the moon. And the program that fires here is program 63. So if you remember, they're punching in these programs, and the command module navigator, which in the case of Apollo 11 was Buzz Aldrin, is responsible for entering the programs. And these programs actually have names, though the astronauts weren't always aware of them. The name for program 63 was Burn Baby. What this does is it controls the brake. It controls the way that the lunar module brings itself down. And Apollo 11's core set overflowed here. So this was the point where the errant signal from the radar dish, or from the radar dish's cable, not even the radar dish, caused the computer to start flipping out. And they would have aborted. They would have just ditched the stage and then gone back had someone not been an expert in the obscure warnings of the computer in mission control. So they just kept flipping things off until suddenly the computer was capable of doing its job. So program 64 pitches the craft. So pitching the craft is inefficient. So the most efficient thing to do would be to have the astronauts sort of lay down and not pilot at all and have the craft bring itself in automatically, which the program did exist to do that. But the problem is the lunar module is not capable of understanding if it's going to land on the side of a mountain or not. So you have to have pilots instructing the lunar module as to where to be, even though the lunar module is controlling all of the basic functions of the rocket. So program 64 pitches so that you can stare out of the windows while you're toggling the joystick. So all of the LMs had a potentially fatal bug here, which is actually my favorite bug in the Apollo guidance computer. It turns out that if you fly over a certain crater, there was a radar in the lunar module that told the computer that it had contacted with the ground. There was no sort of other way of telling. So it told the AGC in the lunar module that the ground had been met and it was time to shut off the main engine. And it did this by measuring height. But it turns out that this radar has a flaw. If you fly over a specially designed crater, you can send the signal back that says, great, we've just landed. And then the AGC, which believes the computer, or believes the radar, just assumes that it's true because there's not enough computing ability to say, wait a second, I did not just drop a kilometer. It just shuts off the engine. So if you fly over this crater, your engine shuts off, and now you are descending without control to the lunar surface. The last program to run is program 66, and this steadies the thrust vector. So you come in on this column of fire, and you're able to set how quickly you want to drop. And this allows the astronauts to say, oh, I'm only dropping at, say, 0 meters a second, so I'm hovering. And now I'm going to translate and choose the correct landing site, because the lunar module computer is not capable of choosing a good landing site. It might actually land you on top of a boulder, which was the case in Apollo 12. Had they turned on the autopilot to land, the lunar module would have just set itself on top of a boulder and then toppled over. There was also a nearly fatal bug in this program as well. So it turns out that the thrust vectoring is done through a feedback control system, so a PID controller, if you're familiar with those. And it turns out that this PID controller was not stable. It was almost stable, but not quite. So it was entirely possible, had they not caught this bug, that Apollo 14, which was going to stress the controller more, would have caused the thrust to sort of wildly vector. So as you were landing, when you got within 10 meters, it would wildly vector, you would tip over, and then you would die. But nobody died on the moon. All of the moon landings succeeded successfully. The only one that was lost was Apollo 13, and that was unrelated to the computer. So the AGC is interesting, it's sort of a historical artifact, but why study it? And the sort of reason that I find most interesting to study it is that it was barely possible. So this is the instrumentation unit, so-called, in the Saturn V lift vehicle. It is itself a computer. It computes the path up. It is so large that they decided to make the computer a structural element in the rocket structure. I can stand inside of it and reach up, and I'm a relatively tall person and can't reach the top. It weighed 55 tons, I believe. Something very, very heavy, maybe 5 tons. Few believed that the AGC would ever be dependable, so very few people had confidence in computers. So this is the X-15. It was the research craft that I mentioned earlier. It had an analog autopilot in it, which would occasionally just sort of flip out and put you into a spin. And then the pilot had to just shut it off and fly manually. But yet the AGC was. And sort of the interesting question to me as a research artifact is how? And the way that they managed it was through careful, pragmatic, and empirical engineering. So, their testing was a continual feedback loop. They would make a change, they would put an astronaut in a simulation, and they would see how it would work. And they also would keep building abstractions. So to the limit of the machine, they would build abstractions to get closer and closer to the domain of the problem, so that when they communicated with people who knew what was needed, that they would be able to program almost to the point where they could communicate. So you have this lack of a divergence of mental models. And the AGC is interesting because the techniques that are developed for the AGC are still in use today. So this program, Real-Time C++, discusses priority scheduling, it discusses machines that have weird bit sizes, it discusses many of the things that we've pegged to the AGC in this talk, but it never mentions the AGC, and it doesn't need to, because they're so foundational. It's sort of, they seem like they were just received from the gods. And the interesting thing, in addition, is that the past, of all of our technical achievements informs our present. So everything that we do gives more tools to the future. And we all of us, we sit inside of this great project. And the Victorians would have sort of capitalized it and meant civilization, and in particular Western civilization. But that's not what I mean. What I mean is that the techniques that we develop today, the techniques that we learn, that we teach ourselves to build better things, to build things that are more safe, to build things that meet particular problem domains, are the foundations of our future. So what we build today become the tools of future generations. So if we figure out how to write better software today, even incrementally, then in the future we can get much more ambitious. And I am excited to be here because we are all trying to get better. And I think that's tremendously interesting. So thank you all.